Hello, my name is Robert Murphy. I'm a professor of pharmacology at the University of Colorado, and I have been studying mass spectrometry of lipids for over 50 years. It's a fascinating area to work in. There's a lot of interesting things information you could obtain from using this tool. So I've been asked by Avanti to present some of my thoughts about various aspects of this complex area of lipidomics. And this first video is going to be an introduction to the general concepts of lipidomics and what I think it involves. And at the onset, I might say that everyone has different ideas about this. These happen to be mine. So let's begin this video with looking at general aspects of lipidomic studies. First of all, let me talk about lipids in general. One of the problems with lipidomic studies is people do not realize that lipids are really seven different classes of very different organic molecules. And these have been defined for us by lipid maps. And here are some of the examples: glycerolipids, such as triacylglycerols, glycerophospholipids, sphingolipids, fatty acyl groups, steroids, and prenols. All of these are in the family of lipids, but yet each one has very different properties. This offers this number of lipid families causes a significant challenge that one must address in your lipidomic approach. Now, lipidomics has been compared a lot to metabolomics, and this is what most people think about lipidomics versus metabolomics. In this diagram here, you see they're virtually, the Venn diagram, very little overlap between the two, and they're equally sized pictures. And typically, as you see, what people think about is that you do a simple, maybe chloroform methanol extraction of a biological fluid, and in the upper layer you have the metabolites, the aqueous layer, and the bottom layer, the organic layer, you have the lipids. And so you analyze either the metabolites, the upper layer, or lipids, the lower layer. It's more complicated than that. In my view of what the Venn diagram is this, where metabolomics is really just a very small portion of the molecules one can find in biological fluid, whereas lipids represent a vastly large number of species. I've estimated here over 50,000 species. Now, those individuals studying metabolomics, they are very good at analyzing the components within the metabolomics area, and often it may be 1,000 to 2,000 species, and they can cover 80 to 90% of these by mass spectrometry. Lipidomics, we're not so good. We only cover 2 to 5% of the species within the entire sphere of possible lipid molecules. So right away you can see there's a tremendous challenge that we have in measuring all of these molecules. Now, another challenge is shown on this next slide, which is an illustration of a frequency diagram of the concentration of lipids in plasma relative to the number of species there are in that family. And you can see there are some molecules, some lipid molecules, which are present in millimolar concentrations. These are typically triacylglycerides and cholesterol esters. And those which are present in plasma in picomolar quantities. And typically these are bioactive lipids for which there are G protein coupled receptors, and therefore they're not present at very high concentrations. Overall, this presents then this challenge of being 12 log difference in concentration in all of these lipid family members, which one may use as a target for lipidomic studies. Now, currently there is no technology which can cover this range of concentration, picomolar components present in millimolar concentrations of other lipids. And therefore, lipidomics already, you can see one must be able to divide the lipid sample or the biological extract into areas where you're going to focus your studies to a particular number of lipids. So this is my overview of what the strategy is, given these problems and caveats of trying to study lipids. First of all, you do not enter this area unless you really have a compelling reason. For example, you're trying to study a disease process, or you're trying to understand the function of an enzyme, and so you've generated, let's say, a knockout mouse which doesn't have a particular enzyme, and you want to find out what is the biological response for lacking this particular enzymatic activity in the cell or in the animal. So you may have this as the overriding feature why you went into doing a lipidomic study. So there are some key features of what this lipidomic study is. They're sort of highlighted with these sort of colored structures here. The first part of it, and where you enter into a lipidomic strategy, is you must be able to extract and isolate the lipid from other components in the biological fluid. This is a very critical step, and one where you really affect a major part of the purification of a sample, because typically lipids are present in lower concentrations compared to salts or sugars or something like that. So you're going to trying to remove them, and luckily for lipids, this often involves an organic extraction. Another video will talk about some of the pitfalls one has with some of the organic extractions, but one has various strategies you can use. For example, solid phase extraction, or using an immiscible solvent to remove lipids from other biological molecules. So once you've isolated and prepared your sample for analysis, the very next stage is mass spectrometry. And you're going to use mass spectrometry to gather some information about the molecule, and you want to gather sufficient information to identify the lipid rather specifically, and you also want to have the information be quantitative so you can tell how much of the lipid is present. Now currently there are three major strategies of mass spectrometry that one employs to gather this type of information. The first one is called shotgun analysis. The second, very different method is chromatography-based mass spectrometry, and I've abbreviated that as LC-MS, and then tandem mass spectrometry is MS/MS. And then a third sort of variant of this is targeted mass spectrometry, and we'll talk about that in more detail, about what some of the advantages might be to using a very targeted approach. So once you have obtained the mass spectrometric data, you want to be able to process the data in a way that allows you to identify what is the lipid you are looking at, or the number of lipids you are looking at, identify the class and molecular species of these lipids, and then also get information about the quantity of the material present. So that's a very important part, and we're going to spend some time talking about how one can assure themselves they are identifying the lipid correctly. Now, in doing a biochemical study of a disease, for example, we know there's a lot of biological variation. So in order to understand the extent of biological variation, we have to repeat experiments several times so that one can employ the power of statistics to be able to really make sure that our data is valid, and that we can understand when things are changing, they're changing reproducibly. And once that you can engage in this, you can employ modern tools of informatics such as principal component analysis, linear discrimination analysis, and things like Volcano Plots to allow you to interact with the data a little bit better. And then finally, once one has an idea of what is changing, the identity of the lipids which are changing, one can enter into the biochemical part and understand what are the pathways that are being altered by the, let's say, disease process or the knockout of the enzyme, so that you have a better understanding of the regulation of the lipid biosynthesis. And this is the ultimate goal of the lipidomics approach, so that you can really understand what biochemical pathways are engaged. You can understand, perhaps, initiate flux analysis, understand the cellular role of lipids and their biophysical role as well. So very often with the, back up to the mass spectrometry part, we look at very specific lipids, often with stabilized-isotope dilution technology, in order to have very precise quantitation. So we really have very good understanding of the subtle changes which may occur in the biosynthesis of lipids. On the other hand, the mass spectrometry approaches which are typified by the shotgun and chromatography-based lipidomic studies. We often term them as unbiased approaches in that we don't preconceive what lipids we're going to measure, but we're using tools that have a very wide field of analysis so that we can see many different kinds of lipids by these processes. However, I must say at the beginning, almost all of these approaches are biased to some extent, and one must always consider what assumptions you are making when you are interpreting the data by either shotgun or the chromatography-based lipidomic approaches. Okay, so let's talk about these in somewhat more detail. Let's talk about shotgun lipidomics, and this has been a very popular area to investigate, and you'll see why at the end of this when we summarize this. And this is a way where you take a crude mixture of the lipids, you do not pre-separate them, but you just analyze them directly, typically by electrospray ionization. And this is one of the examples of the data you might get. And so in this study here, we have phosphatidylethynolamine lipids from mouse heart, and they're in the left-hand panel of this slide. And there are 3 different product ion scanning traces, and I'll explain product ion next, but you can see that you can, from the very crude mixture of ions, you can do tandem mass spectrometry of the electrospray ions and specifically identify, for example, 18-1 containing PE phospholipids by looking for the ion 281.2, mass to charge 281.2. Neutral loss scanning can also be used, and that's illustrated on the right side with triglycerides from the same sample, mouse heart. And here the positive ions were looked at, and in which case they've done another type of tandem mass spectrometry, which is called neutral loss scanning. And here they looked for neutral losses of fatty acids, and in this particular case, neutral loss of 282, it's not mass to charge, but just 282 Daltons, will identify the 18-1 containing fatty acids of triglycerides. And they're sort of illustrated on this third panel from the bottom. Now, there are problems which can be associated with these, and that can be illustrated with this positive ion presentation of the triglycerides. You see the 2 major ions are not triglycerides, but they're phosphatidylcholine species, because they also produce very abundant positive ions, and it's hard to suppress their formation. So one can see artifacts present in these scans, and this can lead to some problems. So let me explain some of these tandem mass spectrometry techniques and what we're actually doing here. I know most of you probably know what tandem mass spectrometry is, and this will just be a review for you. So I will explain a little bit about the tandem mass spectrometry that can be employed in these lipidomic studies. And the first one is on that left-hand panel of the previous slide, the product ion scanning. So here we have a triple quadrupole mass spectrometer. And the way it is set up is that the first quadrupole is going to be in the scanning mode, and I put here the scans between 500 and 1,000 Daltons. The second quadrupole is a collision cell where you do ion chemistry, and the third quadrupole is now set to only detect ions of a certain mass, and here it's set at 281 for this particular product ion scanning experiment. So here's the ion chemistry that you see displayed out here. Here's a phosphatidylethynolamine negative ion. It's got the charge on the phosphate section of the molecule. And when you collisionally activate that in the second quadrupole, it undergoes these 2 reactions. And they're sort of illustrated by those red arrows. And what comes out of those reactions are these 2 carboxylate anions, the R2 carboxylate and the R1 carboxylate. And so if one of those is 281, we are going to detect it here in the quadrupole. So that's product ion scanning, and it's based on the ion chemistry of these lipids, that's a unique feature of these lipids, so that's what adds the signature to identifying these molecules. Okay, now let's look at the neutral loss scanning for those triglycerides. So in this particular example, The ion chemistry involved the lithium adduct. They added lithium as an alkali charging ion to make this positive ion. This is one of the examples of a lipid, of a neutral triacylglyceride. And when you collisionally activate it, it loses, by those arrows, it loses the lithium salt of the carboxylic acid to form this cyclic structure here, and that's the product ion. Now, the loss is a neutral loss. In this case, it's not a charge. You look, and so what you have to do is you have to actually link the two sectors of the mass spectrometers to do this neutral loss. Now, there is a confounding ion chemistry that I wanted to briefly mention, and that these lithium salts can also undergo a very similar reaction with the different groups, the fatty acyl groups, and here by the arrows, loss of a different neutral species, in which case it's a carboxylic acid, not the lithium salt. So here we can see the carboxylic acid, and this is sort of a confounding reaction, and here the products are different. The neutral loss is different because one's the lithium salt and one is the free carboxylic acid. Now, these experiments are shown in the next slide in the same mass spectrometer setting where you have Q1 is set a certain mass. It's going to scan between 500 to 1,000. And the Q2 is the collision cell where the ion chemistry is induced. And between Q1 and Q3, you just change what mass it's looking at by an offset, in this case 256, to look at the loss. In this case we're looking at palmitic acid loss. So they're setting, when the setting, for example, of Q1 is 867.8, Q3 is set at 605.8, and if an ion can traverse all the way across, it's detected by the electron multiplier and you have a signal. So that's called neutral loss scanning, one of the neat features of the tandem quadrupole mass spectrometer, which we used in great advantage in lipidomic studies. Here's an example of some actual data using neutral loss scanning that was published several years ago. And you can see they're doing neutral losses of different fatty acids, and this one I pulled out here, the authors pulled out actually, is they claimed the neutral loss of 284 mass units, and they have assigned it the structure of 18,3. And here's all the ions which have 18,3 in them. Each one of these are molecular ions which have the fatty acid 18,3 in them. Now the problem is that neutral loss they were thinking about was the lithium salt, 283, though they called it 18,3, but in actual fact, there's another neutral loss, which is 18,0, which is the carboxylic acid. You see the proton on there instead of the lithium atom. And this is sort of a confounding feature, that neutral loss gives you a summation of both of them, not just one of them. So that can be a problem, and one has to understand what the various caveats might be. So there are advantages and disadvantages of using this shotgun approach. I would say, first of all, the overreaching advantage of this approach is it's easily implemented in any laboratory with a triple quadrupole or quadrupole time of flight mass spectrometer. This is ideally suited for a large number of lipid species which are major within a biological extract. It's not particularly good for minor species because there are so many major species. The availability of seeing small ions, small abundance ions, low abundance ions is reduced, and you tend to focus your attention on the major ions. Newer instruments have high resolution capabilities, such as the time of flight instrument or the Orbitrap based instruments, and these really remove a lot of these disadvantages I mentioned last time with being able to measure the exact mass of the ions, and one can easily measure the exact mass difference between a lithiated salt and a protonated carboxylic acid. So the lipid identification is improved with these high resolution machines when you can get mass accuracies of 2 to 5 part per million mass error. Another interesting advantage is ion mobility. This is a sort of a newer technology, and it can be used to also improve your identification of lipid with the shotgun approach. So the disadvantages of the shotgun are the minor species can be very difficult to detect. If one is measuring, for example, all the lipids in plasma, you're only going to measure those which are present in micromolar to millimolar. You're not going to measure things which are in the picomolar concentration with that approach. The other problem is often biological extracts have sodium and potassium in the extract, and that makes the analysis much more complicated because it adds additional ions, and that can confuse one if you don't consider that these salts may be present. Now, no chromatography is present to enhance the separation of lipids, so you really have to use the observed mass to understand what lipid and to identify that lipid. And so therefore, isobaric lipids can be a real problem. An example I would give is the BMP lipids, which are bis monoacylglycerol phosphate lipids, versus the phosphatidoglycerol lipids. They're totally isobaric. They differ by positions of acyl group location on the two glycerol atoms. And so by shotgun lipidomics, it's virtually impossible to identify them separately. And so one has to say you can identify it's either BMP or phosphatidoglycerol. Okay, so now let's go to the chromatography-based lipidomics. Here we're going to go to this center part here, which I've sort of abbreviated LCMS, which means tandem mass spectrometry of a liquid chromatograph with a mass spectrometer, or liquid chromatography tandem mass spectrometry. And that's a little bit different approach because one institutes chromatographic separation as a part of the analysis. So this is an example of using this triple quadrupole mass spectrometer. In this particular example, we use it in two different ways. I'll only show you one way here where we're just scanning the last quadrupole section, and we're not using Q2 to collisionally activate it. And actually, the data you see in the next slide, we actually scan Q1, collisionally activate, and do product ion analysis of 369 to find cholesterol esters. So we're doing a product ion scan. And the nice thing about the tandem quadrupoles is you change their operations during the course of the lipid study. The modern machine is very responsive and can change its operation mode in the millisecond time scale. So it's not a scale we live in, but it's a scale the computers live in. So it works quite well. So in this case, I'm going to show you an example of a normal phase separation of lipids. So we inject them into the normal phase HPLC column. And typically we're using solvents. So this is methyl tertiary butyl ether and hexane, which does not electrospray because it has no charging ions, not conductive, not electrically conductive. And so it won't electrospray. So we add, after the separation, we add a solvent which contains a salt to make it conductive, and we just tea that in, and so now when it will undergo electrospray ionization, so we can affect separation under normal phase conditions in non-aqueous conditions and add an aqueous modifier at the end, and then we can carry out this experiment. So here's the results of an experiment. You can see the publication at the bottom here if you want to look at the details, in which the first 5 minutes we're doing precursor ion scanning for cholesterol esters, and then we change the mode of operation at a little bit over 5 minutes to just do looking at just LCMS, looking at molecular ions being formed, and you see all these lipids coming out later on. So this is the region here expanded of what the cholesterol esters look like. Each one has its own individual retention time. They're coming off very quickly, so they're not well separated. But you can see there are, let's see, 1, 2, 3, 4, 5, 6 species and one internal standard, and so we can measure all of those there. The other lipids, they look very similar, and I'm not going to show you that, but you'll see them in the paper. The triglycerides are a major peak. They look very bad in terms of the chromatography, but it turns out individual species chromatograph quite well. The problem of the peak looking poor is because there's so many lipid species. There are probably 500 triglycerides under this envelope here. Diglycerides come out as either 1,3 or 1,2 isomers, and cholesterol is a sort of negatively pointing peak because there's ion suppression. It's a major neutral lipid which is coming off down there. Now you can get some surprises in lipidomic studies. Here's a tag along. It turns out to be a prenolipid, ubiq-109, and it comes out quite nicely, and you can measure that. Or if you want to measure phthalates made in New Jersey, they're coming off too because they're always present in our extracts. Now, one of the problems with shotgun was we couldn't see minor species, and these ether triglycerides, that's what this abbreviation means. MEDAG is a ether triglyceride, you really would not identify this in a shotgun analysis because it appears 14 mass units separate from normal triglycerides, and so it's an area where you're probably not paying too much attention, and they're pretty small. But it turns out they have nice identifiable peaks in the mass spectrum, and we can find them quite well. And it's one of the advantages of doing HPLC separation, to separate the complex mixture of lipids which are present, to increase your ability to see other components. So the chromatography-based lipidomics, either LCMS, which I showed you, as well as LCMS-MS, are very powerful, widely used techniques. We employ the separation power of normal phase for polarity or reverse phase for lipophilicity to separate lipids into different molecular species or into different classes. And this improves our ability to identify them and to quantitate them. This is an important feature, as you'll see in my next topic, is that identification of lipids can be a real problem, and this chromatographic step is really an important part of the identification process. It can also improve sensitivity because you're removing major lipids from some minor lipids, and so you can see them quite well. And what's the disadvantage of this technique? Well, it takes a lot of time to do chromatographic-based lipidomics compared to shotgun lipidomics. There's no question about it. Shotgun lipidomics is very, very rapid, but you are sort of trading off this rapidity of analysis with the improved identification of lipids when you put chromatography in. So we think that's, although I've listed as a disadvantage here, it can be disadvantaged because it drives up cost of your analysis and because of the overhead of time in doing this type of experiment. Okay, so what's the third way to do lipidomics? Well, the other way is targeted analysis. And targeted analysis typically is carried out in the chromatography-based mode, where we have chromatography and tandem mass spectrometry. But we have the mass spectrometer operate in a very specific mode, rather specific to optimize the ion chemistry which is taking place during collisional activation, as well as the chromatographic separation, to allow you to really identify the lipid based on how you're running the mass spectrometer. So you really bypass this step of looking at the information to identify the lipid. You go straight to statistical analysis of the data. So let's look at some of the examples of targeted analysis. And what I've chosen is, of course, an area that I've worked in for many, many years, and that's the metabolites of arachidonic acid. And this is an example of, on the left panel here, we have PGE2. It's the tandem mass spectrum of PGE2. It's got a molecular ion of at 351, and when you collisionally activate that, you get these product ions. And so you see it loses water, loses water and CO2. And then it has a nice little fragment ion, 233, which is cleavage of a carbon-carbon bond. So we can draw some ion chemistry of this. Here's the loss of water, the structure for the loss of water. I've lost it from the prostaglandin ring, from the number 11 carbon atom. And here you can see it undergoes this cyclic loss of water, and driven by the loss of CO2 to form this cyclic structure at 271, rather specific for prostaglandin E2. Here is an example on the right-hand side of prostaglandin E2, but now it's got 4 deuterium atoms present in the upper side chain at carbons 2 and 3. No, sorry, 3 and 4. And so you see that deuterium atom will shift some of the masses. 271 goes to 275 because it contains all those deuterium atoms right there. So we can make use of the fact that we know the ion chemistry, we know that what the stable isotope has allowed us to look at this, and we add the stable isotope. This one's not natural, so we add a precise amount of that stable isotope to this sample. So this signal at 275 is known. How much did we add that led to that peak? So therefore, if this is some fraction of that peak, we can actually easily get the quantitation. So here's an example of now multiplexing this. because typically these mass spectrometers, as I had previously mentioned, work in the millisecond time frame. So you can run through ion transitions or ion chemistry quickly within 5 to 10 milliseconds. Maybe you want to go a little bit longer, 200 milliseconds, doesn't really matter. Here's the PGE2 example. The machine was running 351 to 271 to detect PGE2. It does this in a cyclic process. And so the only place where PGE2 came off was this chromatographic peak. Leukotriene E4, we measure by 438 its molecular ion, negative ion, forming 333 in the tandem experiment. And you see it only really comes off at this point right here, and that's the right retention time. And how do we know that's the right retention time? I don't show this data here, but under that peak is the deuterium labeled LTE4, which is exactly in that same place. So we have the deuterium marking the chromatographic elution, and then we also have the ability of knowing exactly how much deuterium we add. This is called stable isotope dilution. So this example of all of the eicosanoids coming out of the peritoneal cavity of a mouse that has been treated with zymazan. And so you can measure in one experiment, you can see you can measure 10. We typically, actually analyze 25 to 30 different eicosanoids, so we get a broad picture of those metabolites for arachidonic acid. This same sort of thing is used in phospholipid analysis, where in this case one might take a phospholipid as the negative ion, collisionally activated, and as I've already shown you in the ion chemistry, you form the carboxylate anion, and for arachidonic acid, that's mass 303. And so this is what you're going to be looking at, is the products of 303. So you use ion chemistry to identify the molecule, and then the retention times. Now, new instruments are remarkable in they can carry out these multiple reaction monitorings or selected reaction monitorings very rapidly. And so it's not unusual and not difficult for one of these new machines to actually measure maybe 50 to 100 MRM transition within one duty cycle. So a duty cycle just means it's going around the circle, keep measuring the list of 100 ion transitions and going back to number 1 after it goes back to 100 and around and around. And you can change the time frames of when you have a particular list which is present. And this works really well with the chromatographic time frame, because very often classes of lipids can be separated, especially if you use normal phase, and so you can actually change the list of ions you look at depending upon the retention time of the lipids which are present. So this is a very complicated slide. It has lots of different ions in them, but I wanted to show you, this is from a paper that recently appeared in the Journal of Lipid Research. And it's an example of some PC lipids in these first two columns, and some PE lipids in the later columns, and the transitions which are being done in cyclic mode here, all these transitions. And in fact, this whole experiment analyzed 960 different lipids, of which I've only shown 66 here. But you can see the ion transition has associated with it a name of the molecular species, because you're looking at, in these particular cases, the specific ions, which are the carboxylate anions from that particular lipid. The very first entry is the internal standard. Here's the internal standard, a PC, which has a deuterium labeled 18.1 in it. This is from Avanti, and you can see we can specifically measure that transition by looking at the formation of 288 from 11.6. So you have tables of these things. They're readily available, and they can be easily loaded into the mass spectrometer operating system, so that it can undergo these transitions for targeted analysis, in this case for 1,000 lipids, so you can make it even larger than that number here. And you can measure then a large number of lipids. So this really comes close to doing the shotgun analysis, because this is actually pretty quick. Still chromatographically based, but the number of lipids you can look at is really very large. Okay, so those are some of the details of how you get the data and the experiments you might devise to optimize performance of your instrument to get data. Let's look at something about identification. And as I have put here, and one that sort of has been very important for me as I look at other people's data. I realize this can be one of the most challenging parts of lipidomic studies, especially if the person is really not very familiar with all of the problems that one can have with lipid identification and lipid biochemistry. And as I've said, there are some very egregious errors which have appeared in the literature, which have been the total misidentification of lipids based on their mass spectrometric data. So let me spend a little bit of time in this pink box here talking about lipid identification. And the first thing I want to point out is this paper by Gerhard Liebisch in Germany, which has a very nice paper with these investigators in Europe who point out where mass spectrometry has its limitations. And these are really important for you to think about. And so when you have, here's an example, this is the structure of a phosphatidylcholine species that turns out to be an ether lipid. And when you do the first level of, let's say, product ion scanning in shotgun analysis, and you look for products of 184, which is very common for phosphatidylcholine, all you measure is the ion 745. And that happens to have the molecular weight of 745. That's the molecular weight, not the ion you're looking at. The ion would be charged one more proton. There's a problem in that, and there could be two species. There could be a phosphatidylcholine with 33 carbons, one double bond, or it could be the one indicated here in this structure, a phosphatidylcholine ether, 34 carbons and one double bond. The difference of course, with these ethers do not have a carbonyl group here, and that adds the extra difference between the number of carbons that you have here. So you don't know what they are. You can say, well, probably you have to, if all you have is product ion scanning with a low resolution machine, you can say it's either PC745, or you have to say it's either PC331 or PC ether 341. Well, that's rather cumbersome, and you haven't identified the 745 very well. You've only identified it's a phosphatidylcholine by the 184, which is the phosphocholine product ion. That allowed you to calculate that there was a glycerol backbone and a phosphocholine attached. You subtracted that from the measured mass 745, and from the difference between those numbers, you can guess it's either 33.1 or 34.1 ether. So how can you get past that point? Well, you have to do either high-resolution analysis. There is a mass difference between these two, a very easily measured mass difference, and high-resolution measurement will allow you to measure that ion as 34.1 ether. So that's good. If you don't have a high-resolution machine, you can do tandem mass spectrometry under the negative ion mode, and you can scan for the carboxylate anions, which are the products of the decomposition of 746, which is the positive ion of this. In which case, you will identify two ions, the palmitate ion or the oleic ion, but not both. You will only get one of those because the other one is an ether and doesn't form a carboxylate anion. So you will only see one carboxylate anion, and you'll be able to say you have maybe 18.1 ester, and that leaves the 16 zeros in ether. You can also interpret other lower abundant ions in the negative ion scan to help you to assign the SN1, SN2 position of this. And so that typically, well, ether lipids is not a good example, but if we go down to this example of this PC33.1, which is a diacetyl compound, you'll see two carboxylate anions, one from 15.0, one from 18.1. And if you interpret the minor ions, maybe loss of the SN2 carboxylic acid or loss of ketene, you can assign that the second position is really the 18.1. So anyhow, there are limitations in what the mass spectrometer will give you, and you have to engage different levels of mass spectrometry to move across this slide to get into more precise identification, in this case, of phospholipids. Now this paper covers other lipid species, steroids, sphingolipids, triglycerides, or other neutral lipids. So it's worthwhile looking at this and seeing to really understand what level are you identifying the lipid. You may only be identifying it as a molecular weight and maybe as a PC or a PE, but nothing else. So it's important to if you identify only at that level, to report in your either in your paper or in the report you are writing at what level you are actually identifying this. Now, there are other ways you can identify lipids from the mass spec data, either shotgun or the chromatography based. And these are using what we call database searching, where they're taking the tandem mass spectrum and they're trying to match the mass spectrum which are stored in a database. And there's various softwares available from the different instrument manufacturers. The one from LipidView, for example, which we've used a lot, has its own database. It's not using other databases with its own proprietary database. It's very good software. The other softwares often use databases which are commonly available. These other, like the open source software, MS-DIO and so on like that. And even databases which are generated in silico, in other words, are calculated. And there appears to be a problem that I've really seen when people are using this, not thinking about the reports which are coming out of these computer-generated database searching. And here's some examples of what I'm talking about. So I've seen reports, and I'm sure you've seen them too, where people report they've identified this phosphatidylcholine plasmalogen 34-1, but they tell you it's stereochemistry. It's got a cis double bond at 1. It has a double bond at 9 in the SN2 position, and a cis double bond, and of course it is the SN nomenclature is the stereochemistry in the nomenclature. Mass spectrometry cannot give you that information, so these are incorrect. The mass spectrometer did not identify that lipid as that species, that chemically defined species. Even though we would like to think it did, it didn't do that. It either defined it as a plasmalogen 34-1 in the lowest example, or if it did tandem mass spectrometry, it was one that had 18-1, but you don't know the position of the double bond, and you don't know the stereochemistry. Clearly, that's also true for the diacetyl compounds. Here we have an example I pulled out of the literature where they identified four double bonds. 4 double bonds. 1, 2, 3, 4. This example is a more complex polyunsaturated phospholipid, and you see they've identified 4 double bond positions, and they do not have this information from the mass spectrum they got. So they're assuming this, and that assumption may be right, but it may be wrong as well. For oxygen substitution reactions on phospholipids or other lipids, very often they will come up with positions of the hydroxyl groups. Well, those are difficult to get, and they probably didn't get that information if it was in a phospholipid. So to get this information, it probably takes additional experiments. For example, one can do tandem mass spectrometry on the fatty acyl groups themselves to get position information of oxygen substitutions. Sometimes chromatographic separations allow you to get that. Ion mobility can. Sometimes you have to go all the way to ion chemistry, derivatization of the molecule with, for example, ozone, which has been widely used, very effectively used, to tag the locations of double bonds. Or more recently, with the Paterno-Bucchi reaction, you can do the same sort of thing with acetone. And these are the ways you can find the positions of double bonds. You still don't know their stereochemistry, whether they're cis or trans, but you'll know what their positions are. So this is what it takes to get positions, and very often the lipidomics studies do not go to this depth in identifying what the lipid is. So therefore, when you report lipids which come out of a database search, be very careful with how they are defining what the lipid is, because you may not have used your mass spectrometer at that level of sophistication to identify that lipid. Okay, so let's go past the identification, and once you are past that, or you have done targeted mass spectrometry, you now have a lipid name, and you also have now the other piece of information out of the mass spectrometer, the abundance of that ion. It could be in counts per second, or it could be microamps, or something like that, some unit that the mass spectrometer is reporting, the abundance of the ion current. So you have that information, and so now what you want to be able to do is to find out, does that lipid change in abundance because of the biochemical process? And so you're going to repeat this experiment several times because of biological variation to be able to apply statistical tools to really understand them. It could be a simple t-test, or it could be much more complicated, such as principal component analysis or linear discrimination analysis. I'm going to show you volcano plots, and there's many other plots, bar and whisker plots and so on like that, which really help you being able to address the data you're getting, because it includes the biological variation based on the mass spectrometric identification and the abundance that you measured. Okay, so once you have this, you're able to get an idea which lipids are changing, and then with that information, go down into your understanding of the biochemistry, of where that lipid came from, how it's metabolized, to really gain some insight, which is why you started this study at the very beginning, to get down here to the end, to really have some insight into the biochemistry of what is happening in this particular set of samples. Okay, so here are some volcano plots, and I'll just show you briefly. This is an example of a clinical study where we're looking at triglycerides in plasma of patients which are either control or those that have NASH. And the volcano plot's a very nice way to do it. It plots the fold change of each species versus the simple t-test, the log base 10 t-test. And you see those which are in these quadrants up here, which have reasonable amount of fold change, and they are highly significant. You look at these ones which are in these quadrants, these ones which are close to the norm, they're not so interesting, so you don't pay too much attention to them, but these up in here you would. This study on the right-hand panel is one where we did the target analysis of the 900 species. So you see a larger number of lipid species, and you probably, if you look very closely, you can see that the wild type animals treated with LPS, there was a lot of BMP phospholipids that were changing in the LPS treated up here, and these are the control on the left side. And if you knock out an enzyme, this is an ACL-CoA transferase that you see the products change because of that enzyme. And here we see mostly PG, phosphatidylglycerol species, are changing here instead of the wild type animals. So this gives you insight into the biochemistry and something you want to think about. Why is the PG changing in this particular case? And that is guiding you into looking at the biochemistry. Now, this is another example of what the data gives you in a lipidomic study. So this is now looking at steroids in the plasma of mothers who give birth either to preterm babies or give normal birth, and looking at these numbers down here of the group has to do preterm, early or late, and this is term birth, early or late. And you see in this particular study, the amount of testosterone was really quite remarkably high in these preterm birth mothers, and testosterone normally is not a very abundant lipid in the plasma of women, so that was somewhat surprising. And even more surprising was when you looked at the actual data, there's a population of plasma levels of testosterone in these women. It averages below a picomole per mil. And there's a few outliers of that. In fact, if you go up 7 standard deviations, it's still below 5. And here's this one sample here that's up here at over 10 picomoles per mil. This is really bizarre. So this points out to to the individual doing this lipidomic studies, there's something very different about that patient. And so you want to think about that. Now, one of the really important things about mass spectrometry is you want to look at the data. So the first thing you would do is say, is this an artifact? Did we mismeasure this? Is this real? So we took a look at the raw data, and here it is. Here's what the raw data is behind this. This is the outlying sample on the left. Here's our internal standard. It's a stable isotope labeled testosterone. It's got 3 carbon 13s in it. You can see it's 292 going to 100. Gives a nice chromatographic peak. And here is the sample, which is so big. It's huge, 42,000 counts per second signal, and it's 289 going to 197. And so that looks real. It's not an artifact. It's absolutely real. Has the right retention time, and it has, of course, the right ion chemistry. A typical sample, much lower, and of course even the internal standard is lower because of the carrier effect of having this much testosterone will change the absolute signal, so that's why we use internal standards. So here you see the internal standard marks the retention time, and there's much less of that sample of testosterone in that subject. So this is real. What does that mean then, if there's so much testosterone in that sample? Well, this is the biochemistry of testosterone starting from cholesterol. Of course, it can start from acetate. But here's cholesterol going to pregnenolone to testosterone, and then it is metabolized to estradiol, the testosterone sulfate, or glucuronide, or dihydrotestosterone by 5-alpha reductase. So when you measure something, you're only measuring a snapshot. You don't know if it's coming in fast, and that's what the problem is, or maybe it's being metabolized slowly, so it's building up. And so this allows you to think about a series of experiments you might do with this individual to find out, why is this person's testosterone so high? There's another trivial example. We don't know about this thing, and this person could be abusing testosterone. They just have a lot of testosterone. They shouldn't do that. Anyhow, this allows you to pick out these outliers, the lipidomic studies. And so that provides insight to the individual patient. So the conclusion of this introductory area is that mass spectrometry-based lipidomics is really a very powerful tool that really can probe biochemical events in complex biological samples, and I've shown you some examples of that. There are several approaches which have been readily employed by a single laboratory, for example, shotgun analysis or chromatography-based, and they're easily implemented, and one can use those to do very intricate lipidomic studies. Mass spectrometers continue to develop both in their hardware and software, and it's important to keep track of that and to know what the developments are. When I started 50 years ago in mass spectrometry, these techniques were impossible, but now they're readily available to virtually everyone who has a tandem quadrupole instrument or an Orbitrap type machine. Now, I'm going to talk in a later video about relative quantitation, but it has to do with targeted analysis. And this is a way that one can easily go down into the statistical analysis without doing precise quantitation. And we'll talk about that in another video. There are challenges which face all of us doing lipid studies. For example, the number of internal standards which are available to you to buy from companies like Avanti. They're growing, but we need more. Reference standards are critically important. I'll stress that again in another video. And we don't have very many reference standards so that we can generate valid calibration curves. And the last point, to reiterate once again, be absolutely sure that you know to what level you're identifying your lipid when you're using mass spectrometry, because there are limits to what you can claim that you have identified this lipid.